Yeah. So actually, thanks for giving me a chance to present my research. My name is Jong-Hak Woo. I'm working at Seoul National University. Here is a picture of SNU campus from one of these nearby mountain tops. And you can barely see the skyline of Seoul, actually. So I know many of you have been to Japan or China, but I guess not many of you have been to South Korea. So if you have a chance to go through Northeast Asia, you can simply stop by. It's about 2 hours flight from Tokyo or from Beijing, so you can easily stop by if you have some extra time. So just let me know, I can host you. So I'm going to talk about the M-sigma relation. In this program, we heard about M-sigma relation many times, but I will mostly focus on active galaxies. So my talk will be in 2 parts. First, I will talk about today's M-sigma relation at redshift 0. And then I will move on to the second component, which is evolution of M-sigma relation over cosmic time. So I have many collaborators. Here is a list of my students at SNU. In particular, the Daesung Park's thesis is mainly related to the various parts of this talk. Also, I have collaborators here at the UCSB, Tommaso Trell, and also at Irvine, Aaron Barth, and Valda Van Aert, and Matt Markan, and various other people. So I guess to this audience, I don't have to give a long introduction on the M-sigma relation. I will just mention a couple of things. So basically, this black hole mass galaxy property scaling relations imply that somehow black hole growth is fundamentally linked to galaxy evolution. There might be some co-evolution. So basically, this correlations has been interpreted as that there has been some sort of self-regulation between black hole growth and galaxy growth. And obviously, the agent feedback is a very popular topic. And in numerical simulations and semi-analytical models, this agent feedback has been implemented so that agent feedback can explain various problems like cooling flow, galaxy downsizing, and also M-sigma relation. Also, there is other proposal, such as non-causality. If you look at Peng 2007 and Yanke and his colleagues 2011 paper, then they say if you just follow through galaxy merging, then you will naturally see the outcome as a black hole mass galaxy mass correlation. Although in this case you see tighter and tighter correlation as we come to redshift 0. So it's not clear whether this is actually very consistent with the observation. Anyways, I'm not going to go in detail comparing different models, but in this talk I will mostly talk about from observation point of view. So over the last few years, we now have much larger sample of dynamical black hole mass measurement. It's up to 70, 80, depending on who you ask. So people started dividing their sample into different bins. For example, as a function of, depending on the galaxy type, early type, late type, or depending on the presence of a bar, or maybe a classical verge, pseudo verge. Depending on these different characteristics, maybe galaxies and black holes may follow different M-sigma relation, or maybe they are located in different parts of M-sigma plane. So it's quite interesting, but to me, still, this about less than 100 objects is still a very small sample. So at least to me, I don't feel very comfortable to divide sample into different bins, because once you do that, you have very, very narrow dynamical range. So it's quite interesting to look at this M-sigma relation in the present day in terms of the galaxy evolution history. If galaxies are mainly formed through galaxy merging, or maybe they are building up their bulges through secular evolution, they may end up in different M-sigma relations. So the present day M-sigma relation is quite interesting to study in terms of galaxy formation and evolution, also black hole growth. So from observational point of view, we try to study the M-sigma relation today using active galaxies. And the question I'd like to ask is that whether active galaxies follow the same M-sigma relation as inactive galaxies. So the reason is that because all these black hole masses using type 1 AGN is actually partly depend on the local M-sigma relation. So as we know, the black hole mass has been estimated based on this Vball theorem. Here the broad line region size is directly in a sense, directly measured from reverberation mapping, so we know the distance to the broadline gas. And then the velocity is measured from width of emission lines, such as H beta or UV MG2 carbon 4 lines from quasar spectra, and then these two composed of virial product. But still, we need to have this order of unity, the scale factor, we call it virial factor, because what we measure here is that the line of sight velocity dispersion. We have to translate this into three-dimensional intrinsic velocity dispersion. So if broadline gas has spherical symmetric distribution, then this factor could be 3, but actually it may be larger than 3. So we cannot determine this virial factor for individual objects. So what has been done in this field is that basically we match the AGN M sigma relation to a quiescent galaxy M sigma relation. For example, here is the plot from our 2010 paper. So these black points are inactive galaxies for which we have a dynamical black hole mass measurement. So this is, at that time, it was from the Kiltekin paper. And then we have reverberation mapped AGNs. So these black hole masses are from reverberation mapping result based on this. And then we can simply fit the M sigma slope on these red points. So it seems like the AGNs have almost comparable, similar slope compared to inactive galaxy M sigma relation. And then we can actually move these red points up and down and then determine the normalization factor. So this F has been determined based on this matching. So in this case, F was about 5. So it implies that probably broadline gas doesn't really have a spherical symmetry, but maybe it's more flattened disk-like distribution. But since then, over the last few years, actually, there has been some major updates in inactive galaxies and also in reverberation sample too. So the updates of quiescent galaxy sample is that, first of all, we have a larger sample, it's over 70 black hole mass measurements from spatially resolved kinematics. And now we have BCGs, 10 to the 10 solar mass black holes. And also we have very small mass black holes from mega major measurement. And also, secondly, most of these black hole masses in elliptical galaxies have been almost doubled based on the better dynamical modeling. So because of this change, when you fit the M sigma relation using all measurement, actually the slope becomes a bit steeper than we thought. So now it's sigma to the 5th power. And also, if you look at the intrinsic scatter, actually, intrinsic scatter is close to factor of 3, which is larger than we thought 10 years ago. 10 years ago, we thought this may be better than factor of 2, but now we have larger sample, and the scatter becomes a bit larger. And also, as I mentioned, people look at different classes of galaxies and see maybe there's some dependency on galaxy morphology or galaxy types or galaxy mass scale. Also, we have updates on the reverberation sample. Now we have about 50 reverberation mapping measurements, so we can actually determine black hole masses for these type 1 AGN. These are mainly from LIG AGN monitoring project, which Aaron Brass is a PI. And also, Ohio State University group tried a major effort to build up this reverberation sample. And secondly, we have a much better handle on the measurement of H beta line. For example, here, we realized that we need to actually fit various components to get the best H beta line width. For example, here is H beta broad line, and these are 2 or 3 narrow components, but you also see stellar lines here. These are not noise, but actually this is MGB triplet, it's ion line. So all these wiggles are actually stellar lines. So when you fit this with a stellar population model, you can actually fit them. Sometimes H beta is blended with the helium line, so we have to do a very careful job to determine the width of H beta. Once you do that, then this is the residual, and residual is much cleaner. So this is the second thing. And then out of these 50 reverberation mapped black holes, we also have to measure stellar velocity dispersion so that we can put them on the M sigma relation. But actually, we have about half of them. We measure the velocity dispersion for half of them. The reason is For the other half, in particular, like PG quasars, it's very difficult to measure stellar velocity dispersion because the AGN2 host galaxy flux ratio is very high. So we don't really see stellar absorption lines. So that's why we only have 25 objects on the M sigma plane. Even with the adaptive optics with the largest aperture telescope on the ground. But for the future, we probably can get better virial vector based on the velocity resolved time lag measurement, as Aaron Bars last week talked about this. Basically, we can model the broadline gas geometry and inclination, and then comparing with the velocity resolved time lags, we can actually determine the F vector for individual object. So this has been done only for 2 objects so far by Thomas Agrell's group here, Thomas Turrell's group here. But in the future, maybe you can build up this measurement and then maybe independently get the virial vector and compare the M sigma-based virial vector. So once we have all these updates, we can compare the M sigma relation again. In the case of quiescent galaxies, now this is from McConnell and Ma inactive galaxy sample, the red lines. And if you plot all the available reverberation sample, which are red, they seem to have a shallow slope. So one may say they may not have the same M sigma relation. They may be consistent with maybe 2 sigma level. I think there's some problem. As you can directly see, there's some difference in mass distribution. For example, if you look at this low mass regime, then we don't really have many inactive galaxies. The reason is because if black hole mass is small, then you have to resolve smaller sphere of influence. That's why it's hard to measure dynamical black hole masses. Instead, for the reverberation, we don't need to have a spatial resolution. These objects typically have time lag, few light days. It's much easier to do so. So we have many blue points here. Now, if you look at the high mass end, we have many high black hole mass objects from BCGs mostly. But then we don't really have any blue points. Again, this is due to the fact that it's difficult to measure stellar velocity dispersion. Of course, we have reverberation black hole masses larger than 10 to the 9, but for them we don't have stellar velocity dispersion. So that's why there is a mass difference between these 2 samples, roughly factor of 10 mean mass difference between the samples. So this is.
Sorry, what does this guy have 10 to the 9? The AGN.
This one. This one is a PG. I think it's.
Just a PG?
One of PG quasar, and for this one, OSU group measured the velocity dispersion based on Gemini NIFS, IFU. So this is very, very interesting result, but still with AO 8-meter class telescope is very challenging. So once you have a different slope, then it's I feel very uncomfortable because if the slope is different, then how can you justify your virial vector measurement? So what we did here is that we simply do the joint fitting, okay, to overcome this mass truncation problem. So if you define M sigma relation as this, alpha plus beta times log C, then we can put active galaxies and inactive galaxies together and then minimize the chi-square. In the case of active galaxies, we put the virial product, radius times velocity square, and then we put the virial vector here. So we can determine normalization, slope, and the virial vector, 3 parameters all together. So if we do so, we get actually this solid line, which is close to 5 again. So I think the reason being is that probably this inactive galaxy is dominating in their distribution. So what we could do is that once we get the joint fit, and we can calculate the intrinsic scatter again. So once you calculate the intrinsic scatter, the inactive galaxies, active galaxies have almost the same intrinsic scatter. Yes?
At the highest value of the velocity dispersion in black hole mass, I remember that most of the objects are actually radio galaxies, right? Are radio out objects from BCGs with radio lobes kind of thing. And in previous, and you call here inactive galaxies. So I'm confused about this distinction between active and inactive.
Okay, so here the inactive galaxy simply means that the nearby galaxies for which we get dynamical black hole masses based on spatially resolved kinematics, they are mostly inactive. They are not typical seafort, not quasars.
Okay.
I think except two cases. I think 2 or 3 objects are actually the seafort galaxies.
Okay.
But in high mass regime, I don't think there are many really radio loud quasars. These are mostly NGC typical. Yes, M87. The M87 is, I think, this one or that one. Yeah. Right. This is the 10 to the minus 7. So it's not.
Right. Not for this one.
Right. So if you include, so depending on your Eddington ratio cut, and if you allow 10 to the minus 9, even the Milky Way black hole is active galaxy. So, but these are mostly, in the case of Vball sample, they are typical broadline type 1 AGN, not liners, mostly seafort 1s and PG quasars. So that's the distinction.
I guess in a sense, they're measured with different methodologies. Whether or not they're active is almost irrelevant. I mean, it is relevant in a sense.
That's right.
They're active.
Yeah. That's right. So I guess the black hole masses have been determined in very different way. So these guys, the red points in active galaxies, spatially resolved kinematics. And these guys are Vball mapping and the width of broad emission line. So, but still, if you believe this uncertainty error, measurement, then you can calculate the intrinsic scatter. And they have almost comparable intrinsic scatter. It's about 0.4x, 0.445x. So this is a bit interesting. Why? Because this black hole mass is not really true because we use average period factor. The period factor can be different for different individual objects. So the fact that we are using a single period factor meaning implying that probably we should have a larger intrinsic scatter for active sample, but it's not. So it's something has been bothering me over the last few years. Maybe the true. So this average period factor we determined from this joint fitting may not be too far from the true value, or maybe all these type 1 agents they are mostly face on object. Maybe this inclination is very similar. There could be range, but maybe this range is not very broad. So maybe actually the distribution of F factor is maybe very narrow, and the mean is very close to the mean period factor we determined. I think this is the only answer I can think of. But still, it's very intriguing. Perhaps this black hole mass uncertainty in this inactive galaxy sample could have been overestimated. So maybe their intrinsic scatter of inactive galaxy should be smaller. I don't know. Or maybe the velocity dispersion error, and typically they assume 10%. Okay, these numbers are from 1980s and 90s. I don't really know the uncertainty on the velocity dispersion, so I typically assume 10% error. So that might be another source of this interesting finding. Anyway, so again, for future, instead of doing this normalization, we may be able to get period factor for individual object. If we can build up a number of individual objects, then maybe you can compare this with M sigma based period factor. So now you are, I guess, you get curious if we change the slope of M sigma relation, how much we can change the period factor. So this is the one plot. I think the Aaron last week showed this plot in his talk, but basically this is a log scale or maybe linear scale period factor, and this is as a function of slope. So what we did is that we just used 3 different compilations from these inactive galaxy papers, Giltekin paper, Graham, or McConnell paper. Depending on whose sample we use, we slightly get different normalization and slope. Okay. So this is simply due to the sample difference. But now if we use one sample and we try to force the slope changing from 4 to 5, then period factor is decreasing almost by a factor of 2. The reason is that once you have M sigma relation, inactive galaxy M sigma relation, the reverberation sample, the mass range is a bit smaller, right? So if you have a steeper slope, then you have to push this reverberation black hole mass down. So that's why you get a smaller virial factor, okay? So this is about factor of 2, from 4 to 5. So keep in mind that this virial factor is not final. Whenever we have a new updates on the inactive galaxy and simulation, if the slope changes, then we get slightly different virial factor.
Right.
Yes.
I'm not completely clear. So here you took, say, let's say McConnell and Hall.
Mm-hmm.
You have 3 dots.
Yes. So these 3 dots are actually 4 dots.
Okay.
The 4 dots, they are depending on different fitting method.
Okay, but so you fit the sample to get. So it's not clear to me if you fix the slope to be 5 exactly,
Mm-hmm.
or you fit the sample, you get a slope self-consistent.
So these points are actually based on using these 3 samples, depending on which fit we have. And this line is we just forced the M sigma slope is changing. So it's not based on the sample. So
you fix the slope to say 5.
but if we fix the slope 5, then we get virial factor about 5. If we shallow the slope, we force the slope shallower, like 4, then we get the virial factor 8. So again, when you have a distribution of inactive galaxy sample, like M simulation, it's like this, right?
No, I mean, I understand what you're saying.
Right.
What I don't understand is if you take this, so the Gültekin et al. In fact, their slope was close to 4.
That's right. This is Gültekin example.
What we're seeing here, the slope that you would fit self-consistently from the sample is 4, but then if you force it to be 5, you have to.
So difference among these 3 samples are difference in the sample. So depending on the black hole mass and what object you include or not, if you fit M simulation, depending on the samples, you get exactly these numbers. Okay. But then now let's forget it. Now let's take this McConnell sample is the best one. So based on the fit, we get the slope of 5. Okay. Then let's force the slope shallower or steeper, and then compare with the reverberation sample, see what kind of virial factor we get. So that's this red line means. Okay, so this red line doesn't depend on the sample. This is simply we just try to do the Monte Carlo simulation. So again, this is one of the reasons why it's difficult to say.
So the point of this exercise is, I guess, to show how sensitive
The virial factor.
The appearance of the average virial factor is based on the actual,
Yes.
Your favorite today best
Right.
fit
Yeah.
sigma. So if
Yeah.
tomorrow then sigma, the fit slope when sigma varies because you add an extra point,
Right.
you can change the actual virial factor by this much. Is that
That's right. So there are 3 things in this test. First of all, we want to test how much variance we get on the virial factor if we choose different samples.
Yeah, exactly.
Okay, and then we get
For
different.
instance, one thing is that the Gültekin
Mhm.
and the McConnell samples seem
Right.
to have, they're more clustered in terms of the slope
That's right.
with different methods, but
That's
the
right.
gram, if you start using the same sample, which is the gram, and then different fitting method, you already start
That's
getting
right.
different slopes,
Yeah.
which is not good.
That's right. So the second point here to compare, fitting method is that basically we get same answer. And if you look at this paper, we actually try to include different uncertainty on stellar velocity dispersion. Everybody assumes like 10%. If you increase that, actually we get different answer among even these fitting method. But if 10% or less uncertainty, then we almost get the same answer, whatever fitting method you choose. This is second lesson. And third lesson is that whatever best sample you have, then let's see how much virial factor change as a function of the slope. So that's the red line. So there are 3 lessons we learn from this exercise. Okay? So the main the lesson you can take home is here is that we cannot simply compare dynamical black hole mass measurement with the reverberation mass measurement, because they're so different, and depending on the virial factor. So it's very difficult to directly compare dynamical black hole mass with reverberation sample. Also, it's very difficult to study cosmic evolution if you are going to use AGN black hole masses at high redshift, and then compared to local inactive galaxy, then virial factor matters. But if you have local AGN M simulation and then high redshift M simulation, then you can actually study them because all of them, we use the same virial factor. So the evolution will be virial factor independent. So I will get back to that point in the second part of my talk. But anyway, just one thing I want to just mention about inactive galaxy M simulation is that, again, this stellar velocity dispersion. So now we have like more than 70 objects here, and black hole mass has been very carefully determined based on updated dynamical model and more careful and higher resolution. But stellar velocity dispersion actually is not actually uniformly measured. They are collected from literature. The measurements are, some of them are 1980s, 1990s, and the data quality is very different. So it's very hard to constrain intrinsic scatter actually. The other thing is that there could be rotational broadening in the stellar absorption line when you have a very strong rotation velocity. So this thing has to be taken into account. So what I mean by that is that, for example, here is the NGC 3227. This is C421 galaxy, for which we actually have the reverberation black hole masses, for example. Then if you measure velocity and velocity dispersion as a function of radius from 0 to some outer part, then you clearly see the rotation curve. So this is sort of a late-type galaxy in the disk, plus minus 100 kilometers per second. Then velocity dispersion is decreasing, so it's typical. So let's ignore this uncertain point here. So typically, velocity dispersion is decreasing outwards. So if you use just single aperture to extract 1D spectrum, and then as a function of aperture size, you get larger and larger velocity dispersion. Because if you are including more rotation components as you broaden your aperture, then you are including blue shifted redshift components. So you get rotational broadening in your absorption line. So that's why you see this kind of trend. So what has been done in this spatially resolved measurement is that you measure these two, and then you integrate from 0 to effective radius, and then calculate the effective velocity dispersion. So in this case, you use the luminosity as a weight, but then you add velocity to velocity dispersion. So that's been done in most of these M sigma papers. Basically, at each point, you are adding velocity and velocity dispersion and velocity, and then you build up your integral. Now, in this case, if you imagine you have a twin galaxy, let's assume a big disk, small bulgy galaxy, twin. One is phase-on, the other is edge-on. Then in a phase-on case, you don't really get this velocity because it's phase-on. Edge-on case, you have a maximum velocity. So if you use this integral for these two twin cases, you end up with a very different effective velocity dispersion. So this is something I worry about. So instead, we could actually get rid of this velocity and simply calculate velocity dispersion using this profile, and then get the effective velocity dispersion. So to test this, actually we did the long slit measurement. This is actually Wollang Kang's her master thesis. We got the Paloma triple spec data for about 30 elliptical galaxies in the M sigma sample. We started this 2008. So at that time, the M sigma sample was much smaller. So this was actually at that time representative object, but not anymore. Anyway, so we did all this H-band stellar absorption fitting and determined the velocity and velocity dispersion as a function of radius. So you can see here, these are all elliptical galaxies, but 80% of them show rotation component at the center. This is not new. All the Sauron project, they discover fast rotator, slow rotator, things like that. So for example, in this case, you see relatively strong rotation out to maybe plus minus 200, and then this is a dispersion like this. So if you add these two and calculate the effective dispersion, or simply you use this one, ignoring that one, and calculate the effective dispersion, you get a different answer. So if you do so, this is the before and after this rotation correction, okay? Then we get roughly 10-20% correction. So if you don't add this rotation velocity to the velocity dispersion, we get smaller velocity dispersion. Now, in this case, these are mostly early type galaxies. Early type galaxies have a big bulge, relatively small rotating disk. So maybe this effect is not large. So if we simply plot M simulation before and after this correction, then all these velocity dispersion measurements getting a bit smaller, 10-20%. And then the slope is getting slightly smaller. It doesn't affect much. So we did this test for early type galaxies, but I guess that if we do this same test for late type galaxies, for which velocity rotation is very strong compared to velocity dispersion, then this rotation effect would be very, very strong. So this is something I worry about, and I wanted to do this test also for late type galaxies. So let me just summarize the first part of my talk. Okay, so apparently if you compare AGN sample, then AGN sample seems to have shallower. Sorry. Okay, sorry. I'm speaking too fast.
So it seems like the most obvious thing to do. Why is it that they started off with adding them in quadrature? It must be obvious for them.
It's not very clear to me. I think that if you want to include all the gravitational potential, for example, the rotation is also gravitational potential, right? So if you want to know the whole gravitational potential, you maybe want to add velocity and velocity dispersion together. But if you only want to focus on bulge component, pressure supported system only, then you want to get rid of the rotation supported component. So that's what we are doing actually. So this doesn't really matter for elliptical galaxies. And so the fundamental plane, all this Fiber-Jackson relation, all these things is probably doesn't really matter. But what matters is that late type, big disk, small bulge systems. Yes.
So the analogy that you just proposed between the potential well and the bulge is similar to what we can imagine the total galaxy luminosity and
Exactly.
bulge
Exactly.
luminosity.
Right.
So if for the same galaxies, have you looked at plotting black hole mass versus the first and the second versions of the star, and again the same black hole mass against galaxy mass and bulge mass, do you get similar trends?
Well, actually, we don't have this one for late type galaxies. It's not available. So these velocity dispersions have been collected from literature mainly. So here, we've done this for 3D object. So the red point.
If you have rotation,
it should be available in principle.
Yeah.
So I talked to Nicholas McConnell, and he sent me his number for his BCGs. And then I talked to Keihan Giltekin. So he's supposed to send me his updated Stellaklosty version. Yes. But then their sample is mostly massive ones. And this the late type galaxy, low mass ones, the pseudo-bulge things, this is not available actually. I try to look at all the individual papers. I sometimes see velocity dispersion profile, the radial profile, but I have to read from the graph for this one paragraph. But you still need to have a luminosity weight, so it's very difficult to do.
Related to that, you want to say that when the simulation people plot, they say these measurements equal to new measure.
That depends.
So it's not a
It's very. So I can say what we do. So for instance, Sander, my group, we do the latter. So actually there is a bulge composition,
Okay.
and that's what we do.
Yeah.
And we found, actually we never published this, but originally we were just measuring the velocity dispersion, everything that you have there. You take all the stars, the way they move. And there's a huge difference. I don't remember how much %.
Okay. That's interesting to
And for
compare.
cosmological simulations, using one or the other made a huge difference.
Okay.
In the end,
I see.
that one is.
Yeah.
However, a bulge disk decomposition itself is not trivial unless very
Right. Yeah.
galaxy.
So from theoretical point of view, I couldn't say this is wrong, this is right. This could be right, also this could be right. But if you use this one, what I worry about from observational point of view is that inclination. So if you have, let's say you use this one, this is perfect because you use the gravitational potential, the total potential. But then if disk is edge-on or face-on, you get different answer. I think that's really bothering me. So I think at least from observational point of view, probably this may give us much tighter simulation.
Also, if your purpose is to calibrate the single level calibration.
That's right. That's right. Yeah. 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 Yeah.
Function.
So this is something also Tommaso group is doing with Valda, Bernard, and we're working together for the local active galaxy with 100 objects. We get this spatially resolved measurement like this. We measure Brodi's boson this way, and we redefine M simulation for local active galaxies. So that based on that, we can study evolution using high Z object. But this is something.
Sorry, before you move to a new
Yes.
topic,
Yes.
I have another question. So here you showed everything as a function of gross dispersion.
Yes.
So it was the one variable, it was the one parameter.
Among other galaxy properties.
Yes.
Yes.
So I don't know if this has been done, but using, for instance, bulge luminosity,
Yes.
you
Right.
get the same F?
That's a very good question. So this is something which I had thought about, but Brodi's boson in a way it's much more straightforward to measure. In the case of bulge luminosity, you still have to use HST images to subtract the PSF, and also you have to do bulge discrete decomposition. So
Yeah, but here you're relying on sigma measurements and date back to the 80s.
I mean, not all. I mean, some of them, right? Some of them, not all. So I think that you're right, and I think that my answer would be, first of all, the bulge luminosity measurement for this reverberation sample is not. It is some problem. I think that I talked to different people who did the bulge disk decomposition for reverberation sample. They get different answer. If you look at the Misty Ben's 2013 paper, they did PSF subtraction and they measure bulge and disk. And if you talk to other people who did the exact same thing, they get different answer. So in a sense, observationally, it's much more difficult to measure bulge luminosity, and we still I would say we still do not have a consensus on that. So that's why it's hard to use ML relation to get the virial factor.
In principle, you could have the same issue. If someone else went and redid your analysis, they might actually, because they fit the line differently, they may or may not.
It's possible. Yeah.
I mean, the principle is applied.
It's possible, but I would say it's still straightforward. Your modular measuring is a line dispersion, second moment of the stellar absorption line. It's very straightforward. But then in terms of bulge, when you look at the HST images, for example, if you look at the recent HST analysis, you have one PSF, two surging index 4 components, and then surging index 1 components. So if you have multiple components, then I don't know, you have to maybe combine these all surging 4 components, or whether your fit is wrong. It's very hard to interpret it.
There is more room for.
I think it's much less straightforward, I would say. So this is something, I think you're absolutely right. We want to do independent, not absolutely independent, but we still want to do ML relation and get the virial factor and maybe compare. I think that's something has to be done. But so far, still observationally difficult, I would say.
But I'm sure there are HST data for all.
Yes, the other advantage of ML relation is that here we only have 25 objects because Brodi's boson we cannot measure for PG equations. But in the black hole mass bulge luminosity relation, we have HST images for these PG equations. You can actually put them here in time and cent. So that's the advantage. Disadvantage is that observationally it's harder to trust this bulge only component.
Well, at least if the same group does the whole thing, you would argue that they're all, at least it's an homogeneous analysis, maybe.
Yeah.
Anyways.
That's right. So let me just quickly summarize and then move on to quickly next topic. So agent sample appears to have a shallow slope, but then if we account for the difference in mass distribution, then we don't really see any evidence that active galaxies have different M sigma relation. So far we cannot claim that active galaxies have different M sigma relation. The one limitation is that for proper comparison, we need to have a same mass distribution between active and inactive galaxies. For that, we need to measure stellar velocity dispersion for high mass quasars. That's still difficult. Reverberation sample is not really representative. So this is something I haven't talked, but it's something for your thinking. So the reverberation sample is in a way, it's a very biased sample. It has to vary, right? Based on variability, we measure time lag. So the reverberation sample on this M sigma plane may not be really representative. In terms of their mass, in terms of their luminosity, they are not very representative. Although there are PG quasars are, sort of between quasar and Seyfert galaxy. So compared to high redshift quasars, their luminosity is much lower. So this is another worry. So we have to extrapolate all these black hole mass estimators for estimating high G quasar black hole masses. So we definitely want to have more genetic agent sample for this study, but so far we are very limited. And video factor thing, I already talked about this. So let me just move on the second part. So maybe I can talk about this maybe in 10 minutes or so. So we want to study cosmic evolution of M sigma relation and other scaling relations. And as you see here, this is present day M sigma relation regardless of agent activity. And this is the today. And then as Martha Valenti's paper shows nice pictures, I just still stole it from her paper. From early universe to the present day, what kind of journey, what path these black hole galaxies are following? So that's the main question. So we wanted to ask a chicken or egg question, whether black holes are growing first and then galaxies grow later, or maybe galaxies are initially growing first and then maybe black hole adjusts its mass based on this gravitational potential of the galaxy. Or maybe they are growing together with a similar efficiency, then we don't really see any evolution of scaling relations. So this is the project I started as a postdoc here at UCSB about 8-9 years ago, working with the Tommaso, and at the time Balda was not here, but the Matt Mark and Roger Blanford. Mainly, we wanted to look at these two specific redshift windows, 0.4 and 0.6. This was chosen to avoid sky emission lines on the stellar absorption feature you are looking for. And actually, this is a relatively low redshift, but their look-back time is actually 4 and 6 billion years. It's a significant fraction of Hubble time. So we have roughly 50 objects, and the main advantage of being here was actually to use Keck telescope. So we use 2 or 3 hours of Keck time to get stellar velocity dispersion for each object. Also, we got the HSD data from ACS NIGMOS 53, so we can get bulge luminosity. Now, we are estimating black hole mass, not from reverberation mapping, but these are they are mainly single epoch based. So instead of reverberation size, now we have to use size luminosity relation. So based on AGN optical luminosity, we infer the size, and then we get the black hole masses. So this is the spectra from Keck. You see very nice broad H-beta line and O3. And as I mentioned, we did all the spectral multi-component decomposition to get the best H-beta line. Now, if you look at this part, you don't really see any stellar absorption line, but if you zoom in, then actually, based on this high signal-to-noise ratio data, you can actually see many stellar absorption features. Then you can fit the line dispersion of it and measure velocity dispersion. So this was the initial result we showed in 2006. For example, at the time, the inactive galaxy sample was about 20-30 objects. Compared to inactive galaxy sample, our distant galaxies seems to be deviating from the local relationship. So if you look at fixed black hole mass, these distant bulges seem to be smaller compared to local bulges on average. So now we have roughly a factor of 2 larger sample, and we actually try to increase the dynamical range. So this dynamical range is only 1 dex. We try to increase to 2 dex. We tried. Now here, instead of inactive galaxies, here we are comparing our sample with the Vball version sample. So the black points are active galaxies too. So we are comparing apple to apple. So in this case, we don't have to worry about virial factor because all of these black mass is based on same virial factor. If virial factor is higher, then everything will move up. If it's lower, then everything moves down. So it's independent of virial factor. So again, we see sort of an average trend offsetting from the local relationship. So if you plot this in terms of black hole mass unit and how far offsetting these objects are from the local relation, then you see this kind of trend as a function of redshift. So here is the Vball version sample. And these are our single epoch-based black hole mass measurement. So on average, you see this kind of trend, okay? And if you calculate this power, this is very strong evolution, okay? So you shouldn't believe this number, okay? It's too high. But the thing is, you realize that we don't really have any object above 10 to the 9. So we are actually looking at intermediate mass scale. And probably this evolution is mass dependent. For example, if we could have chosen more massive object, and they may be evolving like this. So at higher redshift, they are deviating, so black hole grows first. And then at some point, they arrive on the M sigma relation, and you don't really see any evolution. But if you have a maybe low mass object, for example, then they are bending much in later time. So I mean, depending on which mass scale you are selecting, you may see different amount of evolution. So this is actually on average sense at intermediate mass scale. If we include more massive ones, maybe its power would be much lower. So it's kind of, I would say, it's really hard to pin down this evolution as a function of the mass scale, but this is on average scale. So just one last point is that the point you have to keep in mind here is that Vball version sample is based on Vball version result. Our sample is based on H beta and very, very high quality spectra. But this high G black hole mass estimates are based on different lines. So you have to worry about single epoch black hole mass differences. For example, this is all type 1 Sloan AGN black hole masses as a function of redshift. Here at low Z, you use H beta. And if you go beyond redshift 1, you have to use MG2 line. And beyond redshift 2, you have to use a carbon 4 line. Now, of course, the H beta line is best calibrated against the Vball version sample. But still, black hole mass uncertainty would be probably factor of 2 to 3. Now, if you want to use black hole mass based on these two lines, there is additional factor of 2 to 3 uncertainty in this black hole mass estimate. So that's one thing. Secondly, depending on how you calibrate your black hole mass formula, for example, this is work from Taesung Park's paper we published very recently. Against the Vball version H beta mass, we actually calculate the carbon 4-based black hole mass and then come up with the updated black hole mass recipe. So if we compare this with the old Marian Vestergaard Peterson 2006 carbon 4 black hole masses, we see almost factor of 2 difference. So this black line is exact same measurement, but simply we use the Vestergaard Peterson black hole recipe. And this red line is basically we are using exactly the same measurement, but using new updated carbon 4 recipe. Then you see factor of 2 difference. So I would say at high redshift 5, 6, 7, we worry about the black hole mass is maybe too large compared to the different scenarios black hole see it. Maybe this black hole mass absolute scale could be lower and higher. So there's some uncertainty and something we need to also keep in mind. There's one more slide. Sorry, this is the last slide. So what could drive this evolution? Okay, that's the natural, the question we want to ask to understand physics is that, interestingly, 1/3 of our objects show disturbed morphology. Some sort of galaxy merging is going on. So it's about 30% of merging fraction. And this is very similar to the local unbiased swept bat sample. They see 30% of their sample have merging fraction. So even though this is relatively low redshift much below than 1, but still at this mass scale, maybe the merging can play some sort of important role. And through this merging, you could form new stars and build up bulge, but also you could transform this rotation-supported disk into a pressure-supported spherical system. So in a way, you have to grow a black hole too, but maybe the bulge growth would be much more efficient compared to black hole growth.
Are you talking about which phase of the merger you are in? You say that 30% of cases merging plays a role.
So we're not actually this.
There should be merging, right?
So the merging fraction is simply based on their morphology. So at the moment, at the observed epoch, we see 1/3 of them are going through merging, but then the other 2/3 may go through merging over the last 4 to 6 billion years, but we never know. So this is it, and I think I already is 1 hour over, so I will just leave my conclusion here, and then just stop here. Okay, thank you. Any question? It would be interesting to, if we can, from theory, if we can divide the galaxy mass scale, for example, like somehow at low z and high z, if we can follow the progenitor of different mass scale, let's say, as further proposed, like intermediate mass scale, BCG mass scale, dwarf mass scale, and which mass galaxies you have at high z, and then maybe connect them and see what kind of evolution you see in mass-dependent way. That'd be very interesting. I don't know, maybe I'm not sure whether this is doable or feasible, but this is something I want to learn from theorists.
That should also depend on the environment. If you're going to connect, there's going to be a big difference if you're connecting the growth of field galaxies versus the growth of something that started in the field but finished in the plasma.
Yes, of course, yeah.
For the very, very massive one, by definition, we will end up in BCG type.
Right, yeah. I mean, intuitively, you imagine that if you take the galaxy downsizing, the more massive systems are evolving faster, so they arrive on the M sigma relation much early time. In low mass systems, maybe they're still evolving at the low redshift. So you probably see the difference in their evolutionary path. Okay, so no more questions. Thank you so much.